are talking about, like, we've already done the broad zoom out of bonding, okay? We know 3 types of bonding. We have this chapter 11. We have a metal to metal bond, that is a metallic. When we have a metal and non-metal, we have ionic, much like the car. Saturn ionic. That's old. And we have a non-metal to non-metal, which is covalent. Okay, you use this information to determine your naming, right? But now we are going to learn something else. Because if this was all there was to chemistry, chemistry would be quite boring and too easy. Okay, God has created much more complexity here. Because then we look at things like, why does water expand when frozen? Expand. Water. Everything else contracts when frozen, but water expands. Okay. Why?
It's a liquid.
Nope. Everything else can be a liquid too. So, why does water expand when frozen? Thoughts? Concerns, complaints, outrage?
Outrage.
Has to do with something with the shape. So the way the molecules, oh, I moved my car. Now someone's parked back there. See, this is why I park ridiculously right there. Look, there's a truck right there. They're in. What? Well, what if kids are playing out there? They just got run over. Kids just got run over.
Wait, you want a truck, like, that would be great. 10 minutes before we come. Just kidding.
Yeah, dinner.
I know. That's because I had to go procure someone's lunch. Okay, anyways, the reason why it does that is because as it freezes, these are your hydrogens, and then we have the oxygen. They actually go like this. So the hydrogens like link up, and then it creates a larger volume. Why? Because it takes up more space for the same atoms. Okay, but when it's a liquid, they can kind of like fit into each other and fit into a smaller space. Okay, so this all has to do with intermolecular forces. Intermolecular forces. Intermolecular forces are the following: the electrostatic attractions between molecules. Okay, so super awkward. So awkward. Okay, so there are different types of intermolecular forces. We will start with the easiest one first, and these are dipole forces. Okay, here's the idea. You have a compound that has a clear positive side and a clear negative side. An example of this is, well, don't give me an example. That's horrible. It's over. You have no example. You will not learn. Anyways, here's your definition. So, dipole forces applies to polar molecules. Remember, polar means that it has a clear positive side and negative side. If you remember back to our geometries, certain geometries will result in polar ions or molecules, and some will not. Okay, so if you have your tetrahedral, this probably is not polar if all the outside ones are the same, right? But if you have like a linear, you probably have one that is more electronegative than the other. Oh, do you need a pencil?
You
You have pencils or something like that?
Yeah, I've been trying to get rid of them all year.
So just throw them away.
Yeah.
That's
Good
a waste
man.
of resources.
Don't go ahead.
Hey, Ticonderogas, these are the best.
That's
Yeah,
a
man.
waste of
No
resources.
way.
Ticonderogas, man, they're the best ever. Like, that is the best pencil.
I buy that at the dollar store for 99 cents.
No way. The black Ticonderoga, not the yellow ones. The yellow ones don't count. No, the black Ticonderoga. That is I know, it's like the best writing Ticonderoga pencil ever. Okay, where was it? What was I doing?
I remember those pencil tastes. Those
Sorry,
pencil
what was I
tastes
teaching?
so good back then.
Oh, polar. Okay, so tetrahedral leads to polar. Linear leads to polar molecules. Sorry, this is non-polar. If all the outside ones are the same. Linear, definitely polar. What are the other configurations we know? Bent, probably polar, right? You probably have a positive side and a negative side, such as water. This side's positive, that side's negative. What other geometries do we know? Trigonal planar.
Bent 92.
Okay, this guy, probably non-polar, because there's that symmetry on the outside. We got the bent ones already. We got the tetrahedral. No.
Pterodactyls.
Trigonal planar. This is the tetrahedral. What's the one with the little, where it's like, oh, pyramidal. Because it's a pyramid. I was trying to remember that shape. The pyramid. I'm a math teacher. It's okay. So you have this one. This one is probably polar because the top is probably different than the bottom ones. Okay. So when you're thinking dipole, you have a polar molecule. There's a positive side and negative side. And what happens? Well, they align themselves. So the positive end of, that says end. Ugh. One molecule is near the negative end. I just give out a pencil.
Yeah.
Ugh.
I thought I had too much sugar.
Something is wrong. I probably had too much coffee. Okay, so let's take this as an example. You have sodium and chloride, which is the more, or chlorine, which one is the more positive side?
Chlorine. No,
yes.
sodium, because it was.
Which one's positive? Sodium or chlorine?
How do you know?
Sodium.
What kind of charge is it going to take?
Oh,
sodium,
okay.
sodium.
Sodium is going to take a +1, chlorine is going to take a minus, so we expect this to be less electronegative and this to be more electronegative. So if you have sodium chloride, right, you have a bond there, this chlorine is going to want to be near other sodiums. You guys doing okay? You doing okay? Oh.
Right.
Oh, it's like right in the way.
Yeah, like if you were going down, you're going positive.
I know, I could have gone forever, just keep making them smaller. Okay, so the negative side near the positive side. So that's just how they're going to lay out as far as molecules go. Now, if you have a solid, all of this goes away. But if you have liquids, they're able to shift around and move around, okay? So it's a little bit easier for them to orient themselves this way. This really doesn't apply to gases either, because gases are just flying everywhere. They're always moving. So this, we're really talking, I mean, you want to think like liquids, you have those molecules moving, they're able to shift, and they will form these types of patterns. So what's your dead giveaway? That you have a dipole intermolecular force. So within your block of water, when will you have dipole? Well, if you have a bunch of polar molecules, okay? So clearly defined positive and negative. Now, that's great and all, and dipole is probably the strongest of intermolecular forces, but we also have forces called hydrogen bonds. So when you see hydrogen in there, we're looking out for hydrogen bonds. These are a type of dipole-dipole where you have hydrogen. That's boring. So you need hydrogen bonded with either fluorine, oxygen, or nitrogen. So, you need a pencil. Glenn is going soft in his old age. And his youthful age.
Amanda is literally still in his 20s.
His 30s.
30 now?
The depth. Okay, so here is your picture. Again, the hydrogens are going to want to tend toward these molecules. So, although this is how water freezes, most of the time you're going to see something like this. So you have your oxygen and you have your two little hydrogens hanging off of it, right? These hydrogens are going to want to be near other oxygens. You okay?
Yeah, why is
It's impossible to read. You have to write it as I'm saying it.
No, I
Otherwise,
want to say fun. Like
On.
fluorine, oxygen, nitrogen.
Oh, no.
It's like hydrogen bonded with fluorine, oxygen. Oh, you thought school was supposed to be fun. No, hydrogen bonded with uranium is a bad idea. Probably because they wouldn't bond, and also, well, they're both positive, so it wouldn't make sense.
What if you like force them together?
Kaboom.
Is that how that works?
No.
I'm sure nothing happens.
Wait, and how do you
Like, they're not going to bond, because they're both positive.
How do you bond?
They put those elements together.
I thought that's the whole reason why I like because two things do.
I know, but like, you're not going to have, like, the metals will bond with each other, but they're not even bonded. They're just around each other, and then they make, like...
What two elements make?
Okay, moving on. So, this specific version of that... Alright, glad we could have that moment. Finally, the most annoying one is the London dispersion forces. Sir?
Yeah, I'm fine.
No, but you're still talking.
Oh, no, I'm just trying to read it. No.
His brain broke.
He was your
Remember when Ryan first came here, and he was like constantly trying to get like 3 desks together. He was like, this doesn't match my homeschool desk at home. And he like removed like the whole classroom around. So he could have more room. Like people reseated and stuff. Oh man.
I don't remember.
How do you do that?
Oh,
He would mostly do it.
yeah.
Okay, London dispersion forces. These are nonpolar molecules. Fuels without permanent regions. There we go. So, in order of strength, you have your dipole, which means that they are really going to pull together. Then, when you have hydrogen involved, it's still going to orient itself that way, but the force at which it tries to orient itself is not as strong because hydrogen is not that strong when we talk about electronegativity. And then finally, you get London dispersion forces, where you have like covalent bonds going on, so maybe CO2. And you have CO2 around itself, but you still have one side of that that is more electronegative and one that is less. You need me to read it out again? Because my handwriting.
No, I'm
This
just trying.
side though.
Non-polar molecules without permanent regions of electrical charge that attract each other. It's hard to read my handwriting.
No.
I get it. Understand. Yes.
I'm like kind of confused. So what's going on here?
This is how molecules will orient themselves with respect to others. For example, let's take a pairing of students that would be unfavorable for the teacher. Where's this chair?
Me and
Where'd it
Ryan,
go?
mister. Me, Ryan, and Dylan.
Why am I missing a chair?
Put all of us.
All right, here we go. Let's try
Me,
something.
Ryan, and Josiah, and you.
Now I'm good.
Oh, no. It's slow down.
I will talk to anyone.
All right, here we go. Oh man, I was gonna pick on Andrew. Come on.
Great.
All right, so I'm sitting here. All right, yeah. Yeah. Hey, Andrew, how's it going? Hey, yeah. What's going on with this chemistry lesson? I don't know, clue. The teacher did. Yeah, I mean, he did not. Okay, look. What's a fawn? I don't know. You didn't involve right out. He just keeps putting letters everywhere and drawing circles.
Circles are great.
See, Andrew's annoyed, so now Andrew's going to go away because he's like, I can't deal with this guy. But somebody who's really interested in talking to me, come on down. All right.
I knew it! Ron's interested in everything.
How are you, Ryan?
I'm doing pretty good.
Do you want to like stay late today till 4 o'clock and ask questions till the very last minute, student, just for fun? Oh, that's awesome. See, so Ryan and I are going to sit here forever because we could go on for hours or more. Are you sad because you weren't sure? Okay, so like Andrew's over there, he's like, I can't deal with Belinda. So he's gonna orient himself away from the Belinda. And Ryan's like, yeah, let's have an extended conversation together, much like Dylan and myself. And fun test, we have to talk about the email. I haven't applied yet. I haven't made it there. I've been working, I work the recent emails and then well, that's it. Alright, that's all. Thank you.
That's a good analogy, Belinda.
Okay, so like naturally, you're going to have like certain people move closer to you because you want to chat, Dylan. And you have other people who like naturally move away because you're like, I can't deal with them. Okay? That's what the molecules are. You moved away from me. I didn't move away from you. Someone's out. You can't leave.
Yeah, that's actually
Right there. Look. Look. He didn't want to be included in the analogy. No. Okay. Yeah.
Ryan,
What?
I see you.
What?
Okay. Moving on. Here.
He's
Go get a
from
drink.
this
Go
angle.
get a drink.
She's admiring the drawline.
Okay. Fine. So, molecules will naturally orient themselves. This one is the strongest because the electric charge difference is the highest here. Here, hydrogen is not particularly strong charge-wise, so that's our middle one. And then here, the London dispersion forces are the lowest. They will have the lowest amount of force that the molecules have to orient themselves in that direction. Okay? So, now that we've done that, let's. Okay? Are you okay? Is everyone okay? Just go. Just go. Just go. It's like the cap and gown thing. Just don't ask. Just don't ask. Just confidently like stand up and walk out and you're set. But it's like, what question did you ask me? Can we decorate our caps? Don't ask me. Last year they just chose to do it. They did it. Everyone's was appropriate, and then we moved on.
Then permission.
Sometimes.
Oh.
This year's class, I'm highly concerned about a couple of you, so I will check in with you to make sure that you haven't done anything too horrible.
Oh, yeah, I'm gonna miss
Otherwise, I will spray paint the top.
Imagine you just come to the ceremony with like a red pen straight.
Or what if I get like a, whatever the size is, like a 12 by 12 picture of my face and just like put it on there? That would be funny. All right, so we have 15 minutes left, so we should probably get to it. All right, list the type of intermolecular forces. So here's what a problem would look like. I wasn't going to mention any students' names. So you got it. That's good. Okay, so we have this compound. What intermolecular force could possibly exist for this one?
That's whole thing.
You don't even know the two.
So 3 options: dipole, hydrogen bonds, or dispersion forces.
Oh, it might be
Okay.
dispersion.
Dipole. Do I have a polar molecule?
Yes.
Yeah.
Is this polar?
Yes.
The outsides are the same, so it's not polar.
Oh.
Oh.
Okay, the middle is different, but the outsides are the same, so you're gonna have like more positive here, and then the middle is negative. But overall, if you zoom out and look at it, the outsides are the same, so you have a non-polar molecule. So
That's not one of the options.
now that it's not polar, but I just told you that dipole requires a polar, hydrogen bonds require hydrogens, which this does not have, so the only option is the dispersion forces. Okay? Yes? Polar means that there's an obvious positive and negative side. Think of a magnet.
So just positive. Alright.
Yep. And it has to be like an obvious, like this would be more positive this way. But here, you're going to say it would be more positive in the negative, but it only gets one negative, one. So like if there was more negative here, you can't have 2 positives on a magnet. You only get 1. So this is non-polar because it's balanced. But with that said, these oxygens around it would likely orient themselves. Like if you had your middle one, then you would probably have another oxygen orient itself here like that, because there is going to be some attraction there still. And then maybe more oxygens here.
Imagine going to school for this.
Okay, if we like color code, right?
I am. I majored in
Hey,
chemistry.
there's a little smiley face in there.
Okay, so if let's say the carbon is more negative and the oxygen is more positive. I had green at some point.
It's right behind you.
Too late now. I've committed. I've also been committed. No, just kidding. That's something else. So see how the negative sides will orient closer to the positives, even though overall the force at which it's going to do this is not very strong. That's what the London dispersion forces are. Okay, questions on why this is dispersion forces?
Yes.
Yeah.
So, I mean, like, what's like the probability to know that, like, it is dispersion?
It's not ionic.
It's not ionic.
Okay. It doesn't have hydrogen, and it's non-polar. Yeah.
Is the red positive or negative?
Negative. Because carbon is going to be more negative than oxygen.
Carbon is more negative.
Is that true? Do I buy that? I don't know. You'll have to look at the electronegativity chart.
Well, because I think that oxygen.
I feel like I asked.
Okay, so like this, that was not a dumb question. So dipole, you need polar molecules. So it has to have a clear positive and negative. This one has to have hydrogens, and this one is non-polar. Okay. So this goes back to our study in like chapter 5 of polar and non-polar. Okay, does it have an obvious positive and negative side? Yes.
That's the Lewis dot structure, right?
Yeah.
Oh, okay. Because I didn't know if those were just random dots or.
Oh. Nothing's random in this.
Okay.
Except for So Random, which is a television show.
That's so random.
That's
No.
so random.
Wait, what is that? What's the Sunny with a Chance
So yes,
sub?
it's with chance, yeah.
It was So Random. Okay.
That
All
one,
right.
one guy, and then Demi Lovato. Oh,
Yeah. My wife encouraged me to watch that show once.
Really?
Not a fan.
She's like, you should watch Buzzards of Rose. Like,
Okay.
yeah, it's a good show. That's
All right. I don't believe in that kind of
It's
thing.
not. Lemonade Mouth. It'll change your life.
All right. So
Wow. That movie.
how about this one?
Really good.
Okay. First of all, let's practice for Wednesday. What is the name of this?
Hydrogen fluoride.
No. Is it
Fluoride acid. Fluoride?
No.
No,
This is
someone said it.
Hydrofluoric acid.
I only hear two people saying it.
It's
So
called science.
It has to be that. It's that.
hydrofluoric acid.
Yeah.
Okay.
Oh yeah, it does. H in there.
Good job.
Good job, Marissa.
Hydrofluoric acid. Okay. Now, is this polar? Does it have hydrogens or is it non-polar?
Hydrogen.
Oh, look, it has a
Not
hydrogen. So, most likely, it is going to be a hydrogen bond. Hydrogen bonding is a misnomer. It doesn't actually bond anything. It's just that the hydrogens orient themselves toward the other atoms. Okay? Right? Has hydrogen, has fluorine, we're not surprised. Let's try another one. What? Just do it with confidence.
Wait, okay.
Oh, you're assuming it's that.
Mr.
Why is it that?
Huh?
Why?
Okay, bromine is a halogen, chlorine is a halogen, but since there's only two, remember that chart that I just drew like 5 seconds ago with the different geometries? A linear geometry will almost always result in a polar molecule. Why is this polar? Because there's only two things. So even though they're very close in electronegativities, they're not exactly the same. So there is still a positive side and a negative side. So this is polar, therefore we see dipole-dipole. However, because they're so similar, we will also see dispersion forces.
I've got a question.
So this is like worst case scenario. Yeah.
So I missed this because I wasn't good, but there's no bonds.
Nope.
What is that?
They're intermolecular. We're calling them intermolecular bonds,
Okay.
but there's no physical bond there. They just tend to be closer to one another, much like Ryan tended to be sitting closer to me because he enjoyed